Hey guys, I just want to go over rotational symmetry and lines of symmetry really quickly, just to make sure you got a good handle on it. So first, if you were to reflect this red shape here over this line of reflection, or line of symmetry, we must know that each point is equal distance from the given line of symmetry. So for example, if I'm looking at, let's say this point, when I reflect it over, it should be the exact same length. So if this length is 2.6, then I reflect it over, it should be 2.6. So this is just kind of a fun little task to try to see how well you can do to reflect over the line of reflection. But each point is equal distance. So this from here to here is going to be congruent from here to here. And you're doing the same thing on this side. So this is a length of 1, 2, 3, 4. So away would be 1, 2, 3, 4. 3 over, and again, just a fun little task to create your H so that each point of the shape, when it's reflected over the line of symmetry, is equal distance. So like here, this is a distance of 1, then this one would also be a distance of 1. Okay, so the main thing we want to look at is if I give you a shape, you have to draw all the possible lines of symmetry. So if you fold a piece of paper, it has to map back onto itself perfectly. So for a rectangle, we've got 3 different lines of symmetry, 2 different lines of symmetry, which is going to be this fold and this fold. And the main thing that you want to be able to do is actually write what the equation is of that line of symmetry. So here we would have x equals 4.5, and this one would be y equals 2.5. Okay, remember that horizontal lines are y equals a number, and then vertical lines are x equals a number. Okay, moving on from here, we have a square. Your square has 4 lines of symmetry, and that's going to be the vertical line, the horizontal line, and then also your 2 diagonals. And we've got to write the equation of the line for each of those. So for this guy, this would be x equals 2.5. This one would be y equals 2.5. And then for our diagonals, it's a little bit trickier because we have to actually calculate the slope. So for here, this upward slanting one, notice we've seen this line before. So that should be y equals x. And then we've seen this line before, but it's a little bit different in this case because our slope is negative 1 over 1, but this time the b value is going to be 5. So for that downward sloping diagonal line, and let me draw it in blue so you can see it, that would be y equals negative 1x plus 5. Okay? For a pentagon, this is a regular pentagon. So what it means to be a regular shape, so like a regular pentagon, is that each side is the same length. Okay, it's a little tricky to write these lines of symmetry for this one. You're not going to actually have to do that on a test or a quiz. But let's try to draw them. So we have this line would fold over. We can write that one because it's a vertical line at x equals 3.5. And then also, each point to the perpendicular bisector of the opposite side also forms lines of symmetry. So what you're going to notice here is I've got 5 lines of symmetry. Okay, for this is a very important idea, is that if I have a regular pentagon, if it's a regular shape at all, it has the same number of lines of symmetry as it does sides. So a pentagon has 5 sides. That means it has 5 lines of symmetry. Okay, think about like a regular octagon. So for a regular octagon, how many sides does it have? Octagon, there we go. We've got 8 sides, that means it has 8 lines of symmetry. Okay, and then we have our rotational symmetry. So after going through this GeoGebra link, you should be able to rotate What order actually is the number of times it rotates and maps back onto itself within 360 degrees. So for this star, you should notice that it has an order of 1, 2, 3, 4, 5. For the rectangle, it's not a regular shape, but when you rotate it on that GeoGebra mapping, you should have got an order of 2. A square had an order of 4. The cross had an order of 4. The pentagon was 5. The hexagon was 6. The octagon is 8. And what you're starting to notice here is that when we have the regular octagon, the regular hexagon, the regular pentagon, the order this time, so for regular shapes, meaning they have the same length for each side, like a square, the order is equal to the number of sides. Okay? Because the rectangle does not have 4 congruent sides, the order is a little bit different for the rectangle. To determine the magnitude, you take 360 and you divide it by the order. So that's how we find the degrees of rotation. This is going to tell you how many degrees you would have to rotate in order to map your shape back onto itself. So if we have 5 sides, so 360 divided by 5 is going to be 72. So that means every 72 degrees, you have a shape that maps back onto itself. And I can get each degree that I'd actually have to rotate just by adding 72 each time. And we're going to go back to the 360. So 360 does count as one of your degrees of rotation. So basically, to get from 72 to 144, I added 72, I added 72, and so on. For an order of 2, 360 divided by 2 means every 180 degrees I would rotate and map back onto itself. So this order would be 180, add 180, would give me the second degree of 360. Okay, 360 divided by 4, that would be degrees of rotation of 90 degrees, 180, 270, 360. It would be the same for my cross because they have the same order. So different shapes can have the same order, and that means they also would have the same degrees of rotation. Okay, last, 360 divided by 6. So every 60 degrees, you would be able to map the shape back onto itself. 360 divided by 8. Whoa. That would give me 45 degrees. So every 45 degrees, you'd be able to map onto itself. So if I were to ask you to list all the degrees of rotation, like for example, for the octagon, we would have to add 45 each time and get every single degree of rotation that would map the octagon back onto itself. And all I'm doing each time to write these numbers down is I'm just adding 45. And you'll know that you've added correctly if you do end up with 360. Yay! 360. So we've got 1, 2, 3, 4, 5, 6, 7, 8. That's my order. And that's rotational symmetry.